Okay, so we are continuing our review of quantum mechanics and classical optics. So, just a reminder, in the last class we introduced the Heisenberg picture, Schrodinger and Heisenberg picture and interaction picture. I'll come back to them with specific examples, maybe even in this class. But I just wanted to continue this. Again, some of this you've probably all seen in your graduate quantum mechanics, but I'm just reminding you of some of these things, and maybe some of it you haven't. I'll ask if there are some parts that are unfamiliar and we can go a little bit slower. So let's see. So we covered up to the interaction picture in the last class, where we said, we break up the evolution into parts where there is an H naught, which is a piece that we know very well, say harmonic oscillator, two-level atom, whatever qubit that you have, you know it very well, and then you might have some extra piece V, which is a perturbation, which could be an optical field, could be a driving field, could be an interaction with some other atom, for example, right? That will often happen in when we consider quantum interactions and quantum logic gates, that we need to interact two qubits. So then the V can be thought of as the interaction between two qubits, for example. But so we are trying to now understand the time evolution, and so to do that, I just want to come back to the time evolution operator and introduce a couple important expansions or identities that the time evolution operator has to satisfy. So the basic equation for the time evolution operator we saw in the last class, which is that IH bar dt from det naught over dt is governed by the Hamiltonian, which can be in general time dependent. Okay, so H is in general time dependent. The time evolution operator then simply satisfies this operator equation. I didn't derive that actually, so I just sort of assumed it. And what I'll do is I'll just give you notes which follow from this simple sort of relationship, which is, I'm not sketching the whole proof here. I'll just tell you what are the properties that I'm using of the time evolution operator. So if I take any wave state gets psi of t, and I consider its projection onto one of the eigenkets of the observable L, then we know that this can be written as some sum over I that is, first at time t naught, I take the wave, the state ket, and I project it onto a complete set of states, Ki, right there. I project it onto that complete set of states, Ki, and then, which is over here, this is the complete set. And then I introduce the time evolution operator, which takes us from state Ki to state Lj, and that gives us the, so this is essentially the matrix for the time evolution operator, okay? So these coefficients, then this matrix for the time evolution operator is independent of the time t naught, so it gives you the probability amplitude for finding the system in the state Lj if at time t naught it is in the state Ki of these observable, okay? And so we have a couple of simple properties, and using these we can immediately derive that relation that I mentioned earlier. So the first simple property that we expect is that if you go from time t to t, that this should just be the identity operator. Okay? And from a composition rule, which is that we know psi at some time t2, right, must be obtainable from some other time t1 by the time evolution operator from t1 to t2, and psi of t1 itself can then be written as from T1 to T0 times psi at time t0, right? So from these relations, then we can say that time T2 to T1, the time evolution operator, must be the product of two time evolution operators, which is, that's correct. From T0 up to T2 must be the product of these two operators, which is where T1 is intermediate between T0 and T2. So that is a obvious sort of statement, but we are making it formal over here. And from these two, by expanding this relation and so on, for small epsilon, for small times, you can immediately show that that this relationship implies that IH bar dt at time t over t naught must be equal to h of t and t. Okay, so that is how the proof of the relationship comes from. Okay. Okay. Again, I'll give you these notes. Okay, and then that was just to summarize the property of the time evolution operator. And then if we take the adjoint of that, so now I'm looking at some corollaries of this equation, which is that if I take the adjoint of that expression that I just hid over there, which is basically now I take the adjoint of this operator equation, right? Then multiply this equation on the right by t of t comma t naught, not. Gotta be a little bit careful because this is the derivative of this guy. And then also you can multiply on the left by t dagger. You'll get two sets of equations, and then essentially you can subtract the two to get d of. Essentially, we are trying to find the commutator, which shows not the commutator, but we get this relation, right? Okay, so what I'm saying is, if I multiply d dagger times minus IH bar dt dagger dt naught, this one is the equation with t, and then which I hid over here. So I've taken this equation and multiplied on the left by t dagger. Okay. So you can see by taking the subtraction of these two, you get this relationship. And so this again implies unitarity. Or essentially the t dagger and t naught must be inverses of each other, right? Yeah. So what does all this help us with? So now we are going to we can choose some unitary transformation can choose some unitary transformation psi for psi of t is equal to u of t times psi of t, right? So basically, I'm taking a unitary transformation on which I call now psi tilde of t, and then any operator A will transform according to u of t, a u dagger of t. Okay? And if we choose this transformation such that the state vector evolves according to the interaction term, remember that we had h equals h naught plus v, then we can choose this unitary operator u to have the form minus u of t h naught. Okay? And the reason we choose that then is that u of t is simply the same as t dagger from t up to 0, right? Because as I just showed you here, that is exactly the definition of t dagger, okay? And that is for the model Hamiltonian h naught. That is the simple one. Remember, h equals h naught plus v. So, and if this is also subject to the fact that u of 0 is equal to 1, which of course we just also showed for any time evolution operator must be true, then any observable L dagger of t, which transforms according to that relationship, u of t, L, u dagger of t, right? So, by the way, I'm calling that A dagger, or A tilde, right? A tilde in the interaction picture is just u, A, u dagger. So, from this equation, we can immediately calculate the time derivative of any interaction picture operator, which will then go as L of t h naught plus I h bar dou L tilde over dou t. Okay. Whereas the state ket IH bar for this guy will go as u of t h minus h naught u dagger times psi tilde, and we see that the state ket then evolves according to v tilde of t times psi tilde. So this is what I said at the beginning, that if we choose so v tilde here is equal to u, v, u dagger. Okay? So in the interaction picture, the state ket will evolve according to this transformed perturbation or interaction piece, and the operators will evolve according to the original Hamiltonian h naught. And of course, as you know, then when h naught equals the Hamiltonian itself, the full Hamiltonian, then interaction picture becomes equal to Heisenberg picture. And when h naught equal to 0, then the interaction picture becomes the Schrodinger picture. So these are just the two limits of the interaction picture. Okay, so let's do an example, because all of this is very sort of formal and a little bit Have you guys seen the forced harmonic oscillator in quantum mechanics? Have you done forced harmonic oscillator before? Yeah. Let's discuss it. So the example that I'm treating is the forced harmonic oscillator. Just a simple classical system, right? You take a harmonic oscillator and you apply a force to it. we all know that solution from like physics, 1, right? How this is going to behave. Now we're going to do it in the quantum version, okay? So the Hamiltonian for the system is of course our usual Hamiltonian for any harmonic oscillator, right? Written in terms of the canonical coordinates, momentum and position. And then we want a forcing term, okay? What kind of forcing term should we pick? Something that is dependent essentially on the position, okay? So here's the force, right? And that force is basically going to produce something that is dependent on the position in this linear way, okay? So the time-dependent force itself is not dependent on any coordinate. It's just some classical force, think of it that way. But the way it affects the harmonic oscillator is that it creates a force that's proportional, a term in the, it does work on the harmonic oscillator. So force times distance is the work or the energy that the harmonic oscillator is going to be affected by, right? It's just standard description of any Hamiltonian. We can also add some velocity dependent term, right? That's like a damping kind of term, for example, right? Then you would have some other force which now acts on the velocity or the momentum, right? And that is going to act like a damping or maybe an anti-damping force, okay? So these are the two types of forcings that we could right away imagine for a harmonic oscillator. Okay? Everyone is okay with this? Another example of, for example, when you might get a Q dependent piece of the Hamiltonian, if you take an atom and in the dipole approximation, you might have seen that the Hamiltonian will have a term which is proportional to the position, which is also proportional to the dipole moment of the atom, right? Times some external electric field, for example. And that's the most classic example, and we'll come back to it when we treat light atom interactions. Okay, so this is also then useful for understanding that situation. Okay? Okay, I won't go through the details. You can do it in the homework, put it into the homework, which is that if we now use the operators for the harmonic oscillator, A dagger, right, equal to IH bar, and so on and so forth, the classic. I'll write down the definitions later, but we redefine two operators, A and A dagger, in terms of Q and P, which satisfy these commutation relations, and then substitute them back into this Hamiltonian, and I'll let you carry out that substitution. Very straightforward. In the homework, we get the standard harmonic oscillator Hamiltonian plus two terms. Okay? F of t times A plus F star of t times A dash. Where, of course, I should rewrite what this F star, F of t is representing. So I'm basically giving you the answer here, which is so it's written in terms of the forcing forcing functions P, Q, and P. So in homework 1, what I'm going to do is I'm going to ask you to solve this Hamiltonian, the time evolution of this harmonic oscillator, using Heisenberg picture. Right? In Heisenberg picture, then the state ket never evolves, and you just have to solve what happens to the operators Q and P under the influence of a Hamiltonian, which looks like this. And I'll let you do that. I'll write out all the steps for you and give it to you in the homework. Or I'll ask you to work through some of the steps. What we are going to do in this class is we're going to use the interaction picture, and we're going to develop a nice interpretation of these terms. Okay? do that, slide the board here, I feel like there's more light. So clearly we can identify two pieces to the Hamiltonian, right? What is the model Hamiltonian here? Or the simple piece, the one that you all know the solution? A dagger A, right? We know that should be the part that is the regular Hamiltonian. So H naught equals H bar omega A dagger A plus half. Okay? Which implies, if you look back at my earlier statement, that we're going to now apply a unitary transformation which gets rid of this term. Okay? So that transformation is simply e to the I over h bar, h naught times t, which in this case is e to the I over h bar omega, so that cancels out the omega, h bar. I get an e to the I omega, a dagger A, plus half times t. Okay? And this is essentially then the following unitary operator. Okay? Dropping the extra phase term I omega t, it's unimportant. And now what about the interaction piece? Remember, v of t then is the other part, right? F of t a plus f star of t a dagger, and this is the time dependent part. And in the interaction picture, remember, this gets transformed to v tilde of t, which is given by that u of t a dagger a times f of t a plus f star of t a dagger times u dagger. Is that clear? Right? We transform now the interaction term into this new term, which looks like this. Okay? So all of the time dependence, essentially the important time dependence, is in here. And now, of course, you see that we have to evaluate these operator products, which is e to the I a dagger a times t a times e to the minus I a omega a dagger a. Do you guys know of a formula that we could use to evaluate those kind of terms? Do you remember from your graduate quant? E to the a, where a is some operator here, times some operator p, times e to the minus a. Have you remember the name of that formula? Anyone? Or at least you know what it does. It's called the Baker-Campbell-Hausdorff identity. Have you heard of this? Okay, it's also going to be a homework one for you to prove it. So. I'll give you the result. So the Baker, I just call it BCH because that's how it's often referred to, is the BCH identity, Baker-Campbell-Hausdorff identity. And that is that e to the lambda a times b times e to the minus lambda a, right, is equal to b plus lambda over 1 factorial So basically, it has this form of commutator of commutators. Okay? And so, in our case, then we have to evaluate commutators between A dagger A and A dagger A and A dagger, right? Those are the two terms in the Hamiltonian or in the interaction piece. So we need to evaluate commutators of this form, A dagger A comma A. Anybody know what that is? Or how to find it? You can speak up. Even if you don't know the answer, then how would I go about finding this commutator?
Minus A.
Minus A. Very good. Thank you. And if you don't know how that works, then you can ask me later. Essentially, we're just expanding, right? A, B, comma, C is A times B, comma, C plus A, comma, C times B, right? So, and then we also need to use that A, comma, A dagger is 1. Oh, maybe I made a mistake. I said A, comma, A dagger is IH bar. Sorry, it's just 1. Okay. Minus A is equal to A. Yeah. All right. So, and since these guys essentially reproduce, right? So A dagger A, comma A is just minus A, and then we're going to get a minus A here, and it's just going to cancel out with itself because the operator commutes with itself. We get a simple expression which is B tilde of t is equal to f of t A e to the minus I omega t plus f star of t A dagger e to the I omega. Which is nice. So that shows that when you take a harmonic oscillator and you force it with an external term, whether that term is both simply a force that then does some work on the system or damps it, whatever, that can all be written in this sort of very simple looking form in terms of the operators at least, right? The operators essentially just seem to rotate with some frequency A and A dagger, but then there is some forcing function f of t, just a complex conjugate here, that just essentially captures the effect of the force on the system. Okay, so now we just have to calculate the equation of motion for the state kept. So before I do that, let's see if I can skip some of this stuff. Okay. So now we want to calculate what happens to the state. Remember, we were going to calculate for a forced harmonic oscillator what is going to happen to its equation of for the wave function as a function of time. So since we know V tilde of t, basically we just have to solve the motion d psi tilde of t equals V tilde. And to do that, we essentially will use the time development operator, which again comes from knowing the time development operator in the interaction picture and then using this transformation u times u dagger, which will satisfy this equation. So we can clearly integrate this equation, right? So the integral form, right, t comma t1 gives us, we know at time, if this is simply the formula for when nothing happens, then it's just the identity minus this IH bar integral t1 up to t v tilde of t prime from t prime up to t1 dt prime. And then you put that back into the expression again, because we don't know what this is. We can write the same expression for this over here, integrated, and or put this here and integrate it at a second time t double prime, and that will give us a series expansion for the time development operator. And so that is how we would have to evaluate the evolution of the state kept under the action of a forcing term. So we get time t1 equals 1 minus IH bar integral t1 to t. This is the first order expansion which we all usually use, right? This is the first order. We can just take the time development, take the perturbation, integrate it from time t1 up to t, and that gives us the first order. But then we have the higher order terms if we want to be careful and obtain a full solution of this equation. And I might start dropping the tildes after a little bit, just because it becomes painful to keep writing. So this is formally, we can write the solution to this using something called the time ordering operator, right? Again, you may remember this when you did grad quantum. The time ordering operator, which is the most general solution to a time-dependent problem. And what it does is, if you take any two operators, v at t prime and v at t double prime, then what this time development or time ordering operator does, it puts them into time order. Essentially says that if t double prime is lesser than t prime, then it puts them this way, and then if the other way, then it puts them accordingly. Okay? And with that, then this whole expansion that we have here, because here you see we have had to be careful about how we order the operators, because they may not commute in general. Once we have that, then we can just write down the formal solution, which of course may not be very helpful at the moment, but I'll explain to you in a second how to make this a little bit simplified for our particular problem. Okay, so then, so we're going to have. I'm skipping obviously any of these proofs, because there's obviously a lot of questions about how you actually carry out these things. But I'm just going to write down the answer. Hopefully, you've seen some of this in grad point. So there's a bunch of integrals, and because they're all the same integral, we have to divide by 1 over n factorial to get the actual expansion over there. So this is formally written down as the time development operator acting on exponential minus I over h bar integral t1 to t v of t prime dt prime. So it looks simple, but of course there's a lot of complexity hidden in this, and it's not very helpful right away. But we will now use a slightly more manageable formula, which is called the Trotter expansion. Okay, and we are going to use that to solve our particular problem, which was the one where we were trying to solve this expression for the particular case that we had of the harmonic forced harmonic oscillator. Okay, this Trotter expansion, as you'll see in a minute, helps a lot to simplify this entire thing. Okay. Is that? Yeah. So essential idea of the Trotter expansion is that we are going to take the time development operator and just break it up into small intervals, epsilon, which are so small that we can just integrate the potential, that is the V, which is over here, this one, over those small intervals, right? And so the Trotter expansion, basically, I'll just define it, tells us, or states, without any proof here, and it's sort of intuitive, that what I'll do is I'll break up the time evolution from t1 up to t2 into small intervals, right? Each interval is so small that I don't have to worry about the non-commutation of the v with itself over those time intervals. Okay, because the interval is so small that v tilde doesn't stop being commuting with itself. Remember, when we look back at v, it had terms that are both a and a dagger inside it, right? So we can't just assume that at some later time t that v will commute with itself. But we can assume over some very small time interval that the commutativity is, or the non-commutativity is very small. Okay. So all I'm going to do here is expand it in this small time interval. And then v2 is from, so I broke up the time from t1 up to t1 plus 2 epsilon into two intervals, t1 to t1 plus epsilon, and then t1 plus epsilon to t1 plus 2 epsilon. Okay? And that is v of t prime. So we don't need to worry about the whole time ordering business in these intervals, okay, because they're so small. Okay? And the Trotter expansion claims that the entire t tilde now can be written as exponentials of these functions, e to the v1, v2, etc. from any time t1 up to time t is just the limit of n going to infinity of many, many small intervals like this. And we have to show that that would be formally equivalent to that time ordering operator, which I'm not going to do. We'll just skip that proof. But it seems somewhat intuitive, right? That would be a simpler way to solve the entire time ordering business. Okay. So the and if you go, and so to do this, we need to be able to do two of these pairs where v2 and v1 don't necessarily commute with each other, right? Because they are over different time intervals, and the v1 and v2 will not necessarily commute with each other at these different time intervals. Okay, so if we can first find out what e to the v2 and e to the v1 are, then we'll be sort of along the way. And it turns out that we can use the same VCH formula to show that this is given by this expansion over here. Okay? Again, the proof I'll assign as a homework problem. So if you do this expansion pairwise all the way up to n, then it's simple to see that it must look like this. Right? So we'll take two at a time, write this, and then go to the next, and then the next, and the next, and we'll keep doing that. And in the limit of n going to infinity, we'll get this result over here. So basically we have arrived at a result where we just need to evaluate these two pieces, this piece over here and this piece over here. Okay? And remember that those VKs came from these expressions over here, which are basically some integrals. Okay? So in the limit that this n goes to infinity and epsilon, the time that each of those small pieces goes to 0, then effectively this v1 is just the v at the time t prime, and this becomes an integral from time t1 up to t. Okay? As we take the limit of n going to infinity and epsilon going to 0, the first term then looks like what we would expect for the time evolution, which is so integral from t1 up to t of v of t prime dt prime. I'm putting back the tilde to remind us that this was in the interaction picture. Then we're going to get a second term which comes from that second piece over there, which is the sum over all of these guys. And so then there'll be one integral over here, and then there'll be a second integral due to this part. So that is going to give us two integrals, t1 up to t, dt prime, t1 up to t, dt double prime, and with the commutator v tilde of t prime, comma, v tilde of t double prime. Okay, we're almost there. It's a final sort of result coming up. Okay. This is, note that it's a completely, we made no approximations in this solution for what happens to a harmonic oscillator when it is, when there's a forcing to. Okay. So we have to calculate this commutator, v tilde of t prime. So this part is straightforward, right? That's just what you would have expected from any perturbation that acts on a system. But this is the part that is non-trivial, right? This is the part that comes from the Trotter expansion or the full time development operator. And f of t prime, a e to the minus. So now I'm putting back the expressions for v and v prime. Okay, so you can calculate all of these commutators between A and A dagger, pretty straightforward. We get this term. And the first term, which is the integral v of t prime dt prime, also will give us a form which looks like this: minus ih bar integral t1 to t times f of t prime a e to the minus I omega t prime plus f star of t prime a dagger e to the I omega t prime dt prime. And you can see that it will have a term which is proportional to a and a dagger times some integral of this forcing function from time t1 to t, which I will call, there are various notations for this, but I'll just call that times a plus so this is just some number, complex number that represents the action of this force f of t prime from time t1 up to t. Okay. So if be more explicit, this psi, I can never say it right, is t comma t1 is defined to be just minus our I over h bar integral t1 up to t e to the I omega t prime f star of t prime dt prime. Okay, so there's a nice interpretation of this. If we take t1 going to minus infinity and t going to plus infinity, then you see right away this is minus infinity to plus infinity e to the I omega t prime f star of t prime. That is just the Fourier transform of the force. Okay, so this psi from infinity to minus infinity is equal to the Fourier transform of the force f star of t prime, f star of t, which is essentially, we call it as say g of omega, which is integral minus infinity to infinity f star of t, or sorry, f of omega. So in this sort of limit, then the time evolution operator from minus infinity to plus infinity, which is being acted on by this force, has now got a simple expression for it, e to the I beta, where beta was just that first order term over there, and then this term, which is exponential, so we have shown that if you take a harmonic oscillator and you force it, you apply a forcing term which may be dependent in general on both the position and the velocity, then the time evolution of that harmonic oscillator is precisely described, at least from minus infinity to plus infinity in steady state, if you like, by this time evolution operator for the initial state of the system, whatever the initial state of the system. Okay, we don't care about the initial states. And this operator here is very, very well, we will revisit it later on in the course. This particular operator, this part over here, is called the displacement operator. Okay? And which is written as E A dagger minus. And it has some very interesting properties that we'll examine in detail once we quantize the electromagnetic field. But basically what it's going to do is it's going to show us that if you start with a harmonic oscillator in the vacuum state, that is in its ground state, right, where there is no energy of excitation, but still we have a ground state which has energy half h bar omega, and we apply a forcing on this harmonic oscillator. Essentially we drive it with some strength, like we were just showing, then it's going to create what we call a coherent state out of that vacuum or ground state, because we have just shown that any action of a driving field which is proportional to q, the position or the velocity that acts on the harmonic oscillator, can be represented by this unitary operator. Okay? So this operator essentially summarizes everything we need to know about a harmonic oscillator that is being driven by an external force. So this is the full solution of a harmonic oscillator driven by an external force, something that I'm not sure. Have you seen this in grad quantum? Have you? Has anyone seen driving of a harmonic oscillator? You have? In grad quantum? You nodded your head. Have you seen it before?
Yeah.
Oh, okay, okay. Good. Anyone else? No. Okay, good. Something new. I just wanted to not just talk about old stuff, but new stuff. So we will come back to the properties of this operator. All I wanted to show you was why this operator arises in a very physical way. We take a Hamiltonian, we apply some very simple ideas, classical ideas. What is the effect of a force acting on a harmonic oscillator? We know that the force will produce a change in the potential energy, which is just Q times the force, or minus P times the force if it's a damping term, for example. And then we saw in the full unitary, we made no approximations in this calculation, right? We solved the problem right from the scratch, and we got this result which says that the time evolution is given by this operator here, which, as I'll show you later on in the class, represents an operator, a displacement operator, that can create coherent states. And so the effective result is, if you start with a harmonic oscillator, which is in the ground state, and you apply a displacement operator, you're going to create coherent states. These are the natural sort of analogy to a classical force or a classical harmonic oscillator and a classical light field, as you will see later on in the class. So what we are doing here is drawing the connection between quantum mechanics of harmonic oscillators or light fields, as we'll show later on, to the classical optics or classical light fields. Okay, and that's very important when we think about a lot of different problems in quantum information and quantum computing. We have to understand how to obtain different types of states. Okay, any questions about this? Even if you didn't follow every detail of the derivation, I'll summarize it in the notes and give it to you, and you can go through it in more leisure if there are some steps that you didn't miss. But any questions about the physics of it? What is happening? Yes.
Yeah. Okay, so like here, like at the last, you assume the t is approach to infinity.
Yes.
To derive the, it will be like a displacement.
Right.
Operator, so.
Correct.
But like if we have a finite time evolution,
right,
like what will happen to like the?
Well, I mean, the finite time effect is just that it won't be quite as pretty, right? You still get some psi from t1 up to t.
Yes.
It won't be the Fourier transform of the force. That's the beauty of assuming that it's minus infinity to infinity.
Okay.
Because then it's just the Fourier transform of the force. So if you have a pure tone force, you know exactly what the psi is going to be. It's going to be the value of the force exactly at the frequency that you're driving it at. Okay? So in the infinite limit, you know exactly what this is. That's just the amplitude of your term at the pure tone. Okay? If it's just a pure tone. And if it's not, if it's some weird pulse shape, then also it's simple. You can calculate. If you don't go from minus infinity to infinity, and what do I mean by minus infinity to infinity, of course, is once all the transients have died out in a classical picture, right? In a classical picture, it just means when you initially drive some harmonic oscillator, it's going to have some response, then it's going to settle into some steady state. And so basically, that's what I'm describing here, okay? And you can think of it as a steady state. But if you don't go to infinity, then just calculate the integral. Calculate this integral. You know the force F that you are using, and all of these are just some, carry out the numerical integral, and you get the answer. And it's still the same formula here, right? It's just this psi which is given over here, sorry. So it's just psi times A plus psi times A dagger, so that has not changed. Yeah. Thanks. It's a good question. The other term, remember, was just, which is over here, with this V dagger. That just came out to be a simple also, just some phase, right? It's just classical numbers. It has no effect on the operator, right? Because this is just F times Ft double prime, there's no operators left in this commutator. Okay, so that just completely disappeared from the answer. Okay. All we were left with was only this term over here. And that, of course, is because of the very peculiar properties of A and A dagger, right? A and A dagger has this nice sort of cyclical properties that allow us to do this. Okay, so that sort of, I want to talk about some more basic atomic physics, maybe in the next class. I thought I'll give a break from quantum and now go back to classical optics, okay? Because that also is going to something that we're going to feature quite a bit in the courses. Make sure that you have all the basics of classical optics down, which is very simple. We're not going to be doing too much wave equation manipulation and stuff like that, but I wanted to remind you of some of the basic properties of electromagnetic waves, because that might come up again when we're doing some of the quantum optics experiments or theory. So I want to come back to basic atomic physics too, because oftentimes you'll see that when we're doing some problem or we're trying to understand some effect of a electromagnetic wave on a particular atom or something like that, which we might do at some point, then we have to know some basic atomic physics. So I'll come back to that in a bit. But right now I want to switch gears from quantum mechanics, and I realized we sort of went fast through review of quantum mechanics and went into like some more advanced stuff in quantum mechanics. In the classical optics now I'm just going to review very basic properties of electromagnetic waves. Any questions about the harmonic oscillator, forced harmonic oscillator? And you'll get a chance to do some of these parts yourself in the homework. Okay. But I'll take you hopefully step by step through some of these equations. And I'll put these notes also. But as one good thing to know now is that you know the solution to the forced harmonic oscillator. And the reason I say this is because it troubled me as a graduate student. Okay, so that's why I said for this class I have to do this problem. Because when I thought back to my quantum lectures and stuff, we went through a lot of different things. Obviously, perturbation theory, scattering theory, and we did all of that stuff. And then sometime later, I don't remember how it was. Some friend of mine was like, "Okay, so how do you solve the harmonic oscillator when it is being forced by some external force?" And I was like, "I don't know how to do that. I never learned that in classical, in my graduate quantum course." Okay, so I was like, "What is going on here? Why don't I know this very basic thing?" This is the simplest problem you learn in classical mechanics, right? Harmonic oscillator driven by some external force. It's physics 101, right? And then I come to quantum, I don't know how to do physics 101 anymore. And that really troubled me. I was like, why don't we know how to do this? And the reason is it's actually kind of complex, right? We had to do a lot of trickery to get the full solution of the harmonic oscillator when it's driven by some external force. We had to resort to some advanced operator formalism and language And I'm sure there are ways to achieve the same result without doing that. I mean, I think you can also do the same thing in like Schrodinger picture, but it's not quite as satisfying. You don't get this very general displacement operator type result out of it. You have to think about it in terms of, oh, I take this polynomial function and I try to calculate, its integrals and things like that. And it's not as, I think, as clean as this result here. Which gives you a very physical picture of what happens to a quantum state when it is hit by some external force. Okay, so we're going to review basic classical optics. I have 10 minutes, so I'll just start on the very simple stuff. So obviously the main thing that we're going to use is Maxwell equations. And towards the end of this review, I might even talk a little bit about classical nonlinear optics, which has very close connections to quantum optics. Okay, I'm not sure if nonlinear optics was ever covered in electromagnetism here. Did you guys ever do any nonlinear optics when you did Jackson and stuff like that? No. So you did E&M waves, I'm sure, but you never did nonlinear optics. Has anyone seen nonlinear optics in any class so far? Simple nonlinear optics like susceptibility, nonlinear susceptibilities, anything like that? Okay, good. All right, so we'll talk a little bit about that in this class. So of course, in Maxwell's equations, there are two key quantities: the electric field E and the magnetic field B. And in a medium, we also need two other quantities, which is the displacement, electric displacement, D, and the magnetic what do they call it? And H. I forget what this is called. What is the term for it? Does anyone know the word for it? H? It is the one that, of course, is actually proportional to current, right? In Ampere's law, right? So I can't remember whether it's called the magnetic induction or the magnetic flux density or something like that. Anyway, doesn't matter. It's H. We all know what it is by now. Okay. So, and of course, D is related to E in a medium, in a dielectric isotropic medium. D is related to E through this expression, epsilon naught E plus P, where P is the dipole, the electric dipole moment per unit volume. And P is related to E through a quantity which is called the dielectric susceptibility, chi. Again, in an isotropic medium, chi is just a scalar, so it's just epsilon naught chi, or an epsilon naught. Okay, I'm sure you all know what it is, whatever. Write it down. The permittivity of vacuum. Okay, so D then is simply epsilon naught times 1 plus chi times E. Okay. And therefore we define this quantity epsilon r, which is the relative permittivity. And that's equal to 1 plus chi. And so we can also do the same thing for magnetic fields. So I'm just quickly writing those expressions down. And the reason that there's a slight difference between the electric, the expression for the dielectric, where D is equal to epsilon naught E plus P, here it's H equals 1 over mu naught B minus M. And the reason, of course, because H is the one that's actually the one that we can control using electric fields, using electric currents from Ampere's law, and similarly E is the one that we can directly control from the from moving charges around. Okay, so that's just the reason why there is a slight difference in the signs and so on. But this is just the vacuum permeability. Okay, and M again, which is the magnetic moment per unit volume in direct analogy to that guy. The P is given by this expression chi M times H. Okay. So we arrive finally at B then in an isotropic medium is simply mu naught times mu R times H, where mu R is this 1 plus chi M is the relative magnetic permeability, and for most situations, especially at the frequencies at which most classical optics or optical fields are present at, this chi M is going to be essentially 0, and the relative permeability is just going to be 1. Of course, if you are at some frequencies that are high but not quite at optical frequencies, for example, in certain microwave regimes, it's possible to have materials for which this is, you can't ignore this term, and then we have to redo some of these formalism a little bit for that situation. But, okay, so then the Maxwell equations, simply in terms of all of these quantities, again, del dot D equals rho, del dot B equals 0, del cross E equals minus dou B by dou T, that's Faraday's law, and then Ampere's law, del cross H equals J, the current density, plus the term which was given by Maxwell, dou D over dou T, to make the equations symmetric. Okay. So from these equations, then we can immediately obtain that there are these electromagnetic waves. When I said in that there are no free charges and no free currents, rho equals 0, J equals 0, then we immediately get 1 over mu naught del cross B by substituting for H over here as B divided by mu naught times mu R, and mu R I'm setting it equal to 1, so say that mu R equals 1. So 1 over mu naught del cross B equals epsilon naught epsilon R dou E over dou T. And then we achieve you can then take the curl of equation 3. So del cross E equals minus dou over dou T del cross B, and substitute this guy over here. Okay, I'm going to sort of just skip all of those steps. You've all seen this many times. All of this implies for E, you get the wave equation. And similarly, you can derive the equation for B as well, which is going to be exactly the same. Okay? And this gives us electromagnetic waves, right? Because each of these components, Ex, Ey, and Z, for example, would be a wave equation which has velocity v squared equals 1 over mu naught epsilon r. For vacuum, when epsilon r is also equal to 1, then v squared is is equal to 1 over mu naught epsilon naught, which is equal to c squared, okay, the speed of light. All this is pretty straightforward. You've seen it. And then if you do have a medium, then that modifies the velocity, right, because of the epsilon r. So in the medium, v squared equals c squared divided by epsilon r, which implies v equals c divided by square root of epsilon r, and we define this quantity, the refractive index, as n equals square root epsilon r, so that the velocity is equal to the c divided by r. Okay, so I'll stop there. So we'll continue in the next class, finish up the review of classical optics, and then jump into a little bit of the classical nonlinear optics and start with quantum optics. Okay, see you. Have a good weekend. And I'll try to post some of these lecture slides and notes so you can look at it.